So that was hard about the occupancy and the warps and those optimization steps. So I hope we can touch on that tomorrow again in one form or the other. Also, please feel free to catch me this afternoon or this evening if you have any remaining questions. I know those are somewhat confusing concepts, and as I said, now we have a whiteboard there, a flip chart, so that probably can help us to express the thoughts a bit more coherently. Otherwise, at least it makes up for nice pictures. In the next half hour, I'd like to just talk a bit more about the tools. There was talk of the debuggers, of DDT. The CUDA toolkit comes actually with a variety of different tools that might be helpful for your day-to-day work, especially when it comes to performance analysis and optimization. So I'll just cover those briefly. Basically, when you download the CUDA toolkit from the website, you get a bunch of development tools, libraries, debugger and performance analysis tools, and then when you're getting this for a Tesla board, then you also have access to the system management tools. So in the following, I'll just briefly introduce all of those. It's merely to give you an idea of what's behind each one of those names. And you can then later on go out and explore these tools in more detail, or ask questions about what could be done with those tools. So the first set of tools are the development tools. If you've already gotten to know NVCC, there's actually a few more options that we haven't covered yet. So NVCC is just our compiler wrapper that, to some degree, first off, splits the host and the device code. The host code is being handed off to your native host compiler, usually GCC on Linux boxes or CL on Windows boxes. And then it has the device compiler, so everything that eventually runs on the GPU will be compiled by an LLVM-based compiler. If you're a compiler guy, we have actually opened up a lot of this infrastructure. So if you want to write your own front end to GPU device code, if you have your own language that should generate GPU code, you can do that, and we offer LLVM-based library for that. So you can take LLVM intermediate language and spit out our language at the back end. It's also true in the other direction. You can parse CUDA and get it into the LLVM intermediate representation, and then it's up to you to generate whatever binary code you want. So if you have a fancy platform of your own, you can actually make a CUDA to your platform compiler. I'm not saying it's easy, but it's possible. You then have things like options. We talked about the ones for the architecture. There is a flag for turning on debugging symbols. That can be helpful when you use debugger. I would assume that was covered as well. So capital G is just the GPU equivalent to lowercase g for turning on debug symbols. There's also the -- line info option that adds line information to the PTX code, so you can actually much better find out where some piece of code originated from in the source. And this is just if you're really keen on, if you want to play around, you can compile with -- CUDA, and you actually get the stripped down version of the, so you can use your own host compiler other than GCC if you want to. Now, NVCC is the front end that generates so-called PTX code. PTX code is our abstract assembly language that is portable between different generation GPUs. It's not directly interpreted by the machine, so it's not actual binary code, but it's a language that we then can compile into the actual binary code that runs on the machine. But in order to do that, we need an assembler, and so that's PTX-AS. You usually don't need to worry about it, but it can be useful to, if you want to, especially if you want to figure out how many registers you're using. Because when you're first compiling your code from CUDA code via NVCC into PTX code, at that point, the compiler assumes an infinite register file. So it doesn't care about how many registers you're actually using. It's only at a time when you're invoking PTX-AS where you do an actual register allocation, and that's when it can determine how many registers you're using, or your kernel will use. So when you're calling NVCC minus X PTX-AS equals minus V, that's kind of probably the, the single most important part of this slide. With this one, you will get information about the register consumption of your kernel. So it will tell you that it's going to assume that you will need so and so many registers, and it will also tell you how much shared memory you're using and so on. So this can give you some information prior to running, some information about how much, what resources you're going to use. Another tool that can be fairly helpful is at pretty low level, but it can be useful to look into that. It's called KUuptodump. So basically, it allows you to take binary code that was generated for the GPU and back assemble it and spit out the machine instructions. So this is for a given architecture. So once you've compiled it for instance, for the SM35 architecture, you can look at the binary and you see the true SAS instructions. So those are the actual instructions that run on the GPU. Now, why would you want to do that? It can be helpful when you realize that something is just completely wrong, or you want to figure out why do you see such a huge discrepancy between your theoretical performance model and the actual performance. Typical case is you assume that you're limited by memory bandwidth, but it turns out that you're not. What happens? Well, by looking at the SAS, you might figure out that you have a lot of casts between 32-bit floating point and 64-bit floating point. And they can be fairly expensive. So yeah, that can give you, looking at the SAS can help you identify such problems that otherwise are fairly tricky to find. Again, certainly not something to jump into at the very beginning. It's when you're really stuck and you have no clue how to make any progress with any other form, you might want to do that. The other thing is, I've also run into cases where you're compiling something and it's ridiculously fast. It's way faster at the code than you could ever imagine, or based on your theoretical models, you could ever understand why this happens. In those cases, it can also be helpful to look at the SAS because probably the compiler has eliminated tons of your code that, for whatever reason, it decided was not necessary to put in there. That actually can happen. I mean, a typical use case or a typical workflow for optimization is often that you have your kernel and you start to eliminate some parts of it that you think are not useful, right? You want to figure out like where you do a binary search. Which part of my kernel is the most time-consuming one? Well, it can be that by eliminating part of the code, you're eliminating all of or you allow the optimizer to eliminate all the instructions because you're not writing the final result back out to global memory or whatnot, right? So it can easily be that you're ending up in a situation that the compiler says, oh, there is no need to do anything at all. And looking at the SAS, I mean, in those cases, it would even be sufficient to look at the PTX code, but looking at one of the generated codes can actually be helpful to identify that. Again, may sound academic, but can always happen. And then you're not meant to read that, but the IDEs, so inside both the Eclipse edition and the Visual Studio edition, they allow you, they just combine all the different tools together into one IDE. They can be fairly handy. Like you have the profiler, you have some the debugger, and you also have the source viewer. So in theory, the analysis that the profiler can give you can point all the way back to the individual source lines. So the profiler has a, I'll come to that, but it has a built-in expert system that figures out like what is your most likely performance limiter. And it can even say, for instance, that you might run into whatever, shared memory bank conflicts, one of those weird things that, and it can point you to the actual source line where this might happen. So that can be very helpful to have this integrated tool that just allows you to much quicker pinpoint the place where the problem occurs. So I'm personally not an IDE person. I'm much more comfortable with just VI and make files, but there is definitely huge advantages of using these tools. Okay, libraries. I briefly talked about those before, but right, we have a cuBLAS implementation, a BLAS implementation of all of the BLAS 1, 2, and 3 levels. They're heavily tuned, and the cool thing is now that they are both callable from the device and from the host side. Also, there is basically two flavors of the interface. One is a one-to-one Blas API, as you would see in the netlib reference implementation. But there's also a slightly modified version that allows us to do more, gives us more concurrency, for instance, and allows us to do things like use scalars that are known on the GPU as input arguments for the next BLAS call, which the reference implementation wouldn't allow you because the scalars are passed in as actual scalars and not as references. So yeah, there's this second flavor of the Blas API. Also, this Blas API, the second Blas API has some additional calls like a batched dgem. So when you need to do a lot of dgems, but they are not very large, I mean, as you remember from all the previous talks, you might run into a situation that you're simply not filling the device. Now with the batched dgem, you can launch a huge number of matrix products that will execute at the same time. And so this way you have much better chance of fully utilizing the device. So that's for cuBLAS. CoolRun is a random number generator library. Again, if you ever tried to write a parallel random number generator yourself, then you know that this can be a bit ugly. So it's there. No need for you to reinvent the wheel. Just use it. And we have a large set of both quasi-random number generator and pseudo-random number generators. There is different distribution functions that it can generate, so uniform and Gaussian or normal distribution. So that's all prepackaged. And it also has both a host-side API and the device-side, a kernel API. So you can actually call CoolRun from within kernels if you have a kernel that needs to generate random numbers on the fly. FFT implementation. This is also constantly being updated and optimized. It has in FFTW terms, I think we're implementing now all of the expert API, but not all of the guru API. So we have a huge flexibility in terms of the data layout, both on the input and the output side. For instance, if you're into synthetic aperture radar processing, where you oftentimes need to do a transpose of your matrices on the fly. You can do that with a single call to cuFFT. It can do the transposes while you're outputting the results right away for you. So that can be very interesting. So if you have any FFT needs, have a closer look at the documentation for cuFFT. Most likely it's covered. Thrust, mentioned before, but here you have a list of the different algorithms. And so probably the most interesting ones are definitely sort, the reductions and prefix sums. I mean, those are tightly related. And yeah, so those are operations that can be very handy if you need to write them for yourself. Sparse linear algebra. We even now have a MultiGrid library, AMGX, that we just announced at Supercomputing that goes in the same direction. So if you have any particular sparse linear algebra needs, have a look around at cuSparse. The NPP, they are, depending on your application domain, also a very large collection of image and video processing primitives. And that comes right away with the CUDA toolkit. Whatnot, any kind of rotations of 2D arrays, any kind of channel filterings, statistics on the images, and so on. That can all be done within the MPPs. So, and then you have, on top of that, you have math.h, which also grows as with every generation of CUDA. So all the math functions and error functions and yada yada are available on the GPU. Debugging. I don't know why anyone wants to use DDT. There's printf. This one is critical or crucial. It's only available at compute capability 2. So you will have to compile it with your code with minus arch equals SM20 or any number that's higher in order to get access to printf. So if you right now just try to compile a kernel that contains printf without any flags, so just NVCC myfile.cu, it will complain and say that this function is not available. So just add minus arch equals SM_20 or higher, and it will work. Now, printf is an interesting case because obviously we don't have access to the terminal from the GPU. So what happens under the hood is that this data gets buffered, and these buffers get flushed to the host side every once in a while. Basically, whenever you have any kind of heavyweight operation like a device synchronize, or if you have a data transfer, at that point, these buffers get moved back and then are printed out on the host side. So one of the caveats is that the buffer can overflow. It's just a circular buffer, so you might lose output if it's not being flushed often enough, if you're producing too much output per thread. And yeah, keep in mind that you're writing, if every single thread of your million thread grid writes a novel out to standard out, you're ending up with a lot of output. So yeah, the pattern I'm often using is that I'm trying to figure out which kernel or which thread is responsible for whatever, an error that I'm seeing. And then I'm limiting my output to this particular thread. Yes?
So it's not flushed with a new line?
Nope.
And there's also no like flush or something?
No, the only way to flush it is really to have another heavyweight CPU or a CPU-initiated CUDA call. As I said, there is the full list is in the programming guide, but it's basically yeah, device synchronize and so on. So a finite number of different CUDA calls that will cause the buffer to be flushed. Yeah. Yes?
Before you get to talk on the libraries and so on, are there any device-side libraries like Thrust?
Yeah, not really like Thrust, but there's actually an interesting development called CUDA Unbound. The idea there is that Thrust is still at the level of grids, right? So you're assuming that you have large enough amounts of work, and with a single Thrust call, you're launching a new grid. But when you're writing a kernel, there's a lot of small things that you probably want to do that you don't feel like you want to do it over and over again. And so cub fills that hole. So if you need to do a reduction within a kernel, so within a single thread block, you want to do a reduction, Thrust wouldn't be the right tool for that. That's more the domain of cub, right? Because Thrust, again, would spawn a new grid for doing that. Also, if you need to do memory accesses, like fetching tiles from global memory, efficiently fetching tiles of global memory into your thread block, that's another one of those operations that can be done by cub. I haven't put it up because cub is currently not being distributed with the CUDA Toolkit. The reason being is it's still kind of a research and development effort. You can download it. Again, it's CUB for CUDA Unbound. Has very interesting features, and our hope is that eventually it comes into the toolkit. Yeah, it's going to take some time to productize it. Okay, printf debugging. Another debugging tool is Khuddam MJ. As I mentioned, it can be fairly quickly or it can easily happen that one of your threads accesses memory that's out of bounds. And usually what happens in those situations is that you're getting an error, and it says something like unspecified launch failure. So whenever you see an unspecified launch failure, chances are pretty high that you actually have an out-of-bounds access. Again, the unspecified launch failure is basically the equivalent of a seg fault. So Khuddam MJ, fairly similar to Valgrind. It takes a lot of time to run, but it finds all these nasty out-of-bound accesses. It also has a separate mode for race detections. So whenever you have race conditions between multiple threads, and you might end up that you have a non-deterministic result based on just on the timing, on the relative timing, Khuddam MJ can be brought into that mode to detect those. So usually my workflow is whenever I'm writing a kernel and I end up in a situation where I see an unspecified launch failure, the next step is to run it through Khuddam MJ and see where I'm seeing a problem. It's written down here. Again, it's useful to compile it with -G and -line info before you're running Khuddam MJ, simply because it then gives you much more information of where exactly that the error occurs. But it will tell you like which thread in which thread block causes the problem. It will tell you at what line number. And so at that point, it can be fairly straightforward to locate the out-of-bounds access. So hugely useful tool. CUDA GEDBeam. If you don't have access to one of the commercial debuggers, it's also a mechanism of debugging. So you have all the GDB features like breakpoints, like traces. You can watch variables and so on. You can set your focus to a specific thread. You can step through your kernel. Yeah. Again, in some cases, it's just a bit too confusing depending on how many threads you have to actually do single stepping through your code, but it's possible. Similar to the other ones, again, you want to compile with -G option just to get all the debug symbols. Okay, that's for debugging. Profiling. NVVP is, I think, also one of the most useful tools that we have in the optimization tool chain, because it can give you a huge amount of very detailed information of what happens inside your kernel. So you get, it has this so-called guided optimization analysis, which I think I showed you a bar chart of that. Tells you like how much time you're spending in, or how much you're utilizing your memory bandwidth, how much you're utilizing your compute resources. It can also pinpoint you with things like that you have unqualified memory accesses. It can tell you what, like the amount of, if you have bank conflicts, it can tell you those kind of effects. So there's a lot of very detailed information that you can get from NVVP. But it's also useful for just timelines. I mean, all this fine-grained optimization of kernels, that's good, and in some cases very useful. But when you're looking at the large applications, in many cases it's already important just to know, like, when is my GPU even doing something, and when is how big are the gaps, the white gaps between computations that happen on the GPU and everything that happens just on the CPU. So just getting an overview of a Gantt chart of the activities on the GPU, the transfers of data between host and GPU, that can be very useful. So NVVP can give you all this information. Oh yeah, so here I have just a graph. Again, this is part of the analysis tab, where it's telling us like how much we're using the different resources, the compute resources and the memory resources. Yes? You need, so NVVP is just a GUI. NVVP sits on top of the tool I was about to talk, which is NVProf. Now, NVProf needs a GPU, right? This one is the actual profiler. Now, the profiler can just collect timelines. That's kind of the simplest use. But it can also collect so-called metrics. Now, in order to do this analysis stuff, you actually need to have access to the individual metrics. The way to get those is with the flag ---- analysis metrics, and you specify an output file name, in this case just profile. And you can import these files into the GUI, into NVVP, and look at them there. Without, sorry. When you run NVProf without analysis metrics, it will just collect the timelines. So you only will have access to the timeline information, but not to the metrics. Oh wow, thanks. I'm not doing another hour. No. Thank you. Yeah, so this way you, without analysis metrics, you just get the timeline. And so that's useful for an initial cut, if you just want to get the basic information. It will also tell you at that point, like how many registers each one of the kernels is using, what your launch configuration is, so how many threads you have, how many thread blocks, and so on, and how much time was spent in each one of the kernels. But it will not be able to tell you like, yeah, how many floating point operations you had. It will not be able to tell you like how many registers needed to be. Well, let's see. There's a lot of the lower level analysis that is not accessible directly from the basic timelines. So at that point, you need to do the analysis metrics. One thing to keep in mind is that, so what NVProf is, it reads our hardware counters, but we cannot collect all the different metrics in a single run. There would be more metrics that we need than we have counters available. And so what NVVP does, or NVProf as well, is that it replays each kernel in order to collect the necessary data. So that means that the runtime of NVProf, when you're turning on analysis metrics, can go up quite tremendously. So you don't want to do that on a very large-scale application. You probably want to do that just on a mini app, or that's just something to keep in mind when you're running on 5,000 nodes on Daint, that you probably don't want to run a large application this way. If you want to use NVVP on something like 30, it's useful to set the PMI no fork environment variable prior to launching your application with app run. Otherwise, it will just complain that it couldn't find a CUDA application, and NVProf will not tell you anything. And then there's yet another profiler, which is part of the driver. Now, this is really, it used to be kind of the only way of profiling. Nowadays, it's not really necessary anymore. But if you're in a situation where both NVVP and NVProf fail, for whatever reason, NVProf is not yet installed, or it's used an older version, it's just good to know that this mechanism still exists. So this one is driven largely through configuration files and environment variables. So you have an environment variable that says you should profile now. If this environment variable is set, then the driver will just keep track of all the different information or all the different kernel launches. And yeah, the output can also be back imported into NVVP. But so this is really a fallback solution in case yeah, you don't have access to NVProf. Okay, so those were so we had the libraries, we had the profiler, we had the debugger. Now the system management tool, and the development tools. System management tools, as non-root, they might not be so interesting. But if you have a workstation at home and you want to use them, that can be fairly interesting to run Nvidia SMI. That gives you a lot of information about what the GPU currently does. Actually, we also can use that on 30. I think so, at least. Oops. I'm never sure if it's actually in the path or not, but it's somewhere in opt cray Nvidia bin. Oops, default bin. Nvidia SMI. So it's there. Oops. So this can be useful just to figure out if you actually have data, a GPU available. So here you get some information like, yes, on this node we actually have a K20X installed. Something that gets increasingly important is the question of like how much power are we using? Again, you're probably not designing your application for optimal power usage, but it just can be interesting to keep track of what the power consumption is. It can tell you the high watermark in memory consumption, and it definitely can tell you whether you have some processes running. And remember, I mentioned the MPS, so this one server that allows you to, this server process that allows you to have multiple processes share the GPU. This would also show up here as the as a process that is currently running on the GPU. There's even more, so just have a look at the Nvidia SMI man page. I mean, there's tons of information that you can get out of it. Like you can look at the clock rates, at what the device is running. So, yeah, if you have a need for all kinds of detailed information, check out Nvidia SMI. Here, where were we? This one. Yeah, and blink lights, that's definitely a great thing to do with Nvidia SMI. Just if you want to make sure that you're blinking the lights inside the server room here. Now, Nvidia SMI is, again, it's just a front end. It actually sits on top of a library called NVML. And so that's the Nvidia management library. And so this is a C API that exposes all the information that we saw in Nvidia SMI. So if you want to write your own application that whatever monitors power consumption as you go along, that would be the tool to use. Okay, so those are basically the tools. I've just collected here a few more of the tools that are out there. OpenACC you've covered. CUDA Fortran, we haven't talked about this here, but for Fortran programmers, if you don't want to go the mixed language route, there is a PGI version of CUDA that gives you constructs of CUDA inside Fortran. The flip side is that it limits you to the PGI compiler, but still, again, depending on your particular needs, it can be a very quick route to GPU acceleration of your Fortran code. So this is basically it on the tools side. Are there any questions? Nope. All right. Time to do something. We have 45 more minutes to go. You're all on 30. Let's have a look at the examples. You should be able to grab a tar file from this location. I just highlight it here once more. So it's on the project G33. CSCS underscore CUDA 55 underscore transpose.tar. Let me know if you shouldn't have access. Copy it to some location of your choice and extract. Oops. I need to put up a slightly. Yes, hold on a second. Let me do this. So the location is this one here, /project/G33. And then it's just tab complete CSCS underscore CUDA 55 underscore transpose.tar. Okay, and when you when you extracted the tar with tar xvf CSCS CUDA 5.5 transpose.tar, you should get a directory called transpose. And in this directory transpose, there is a directory called hands-on exercise. Now what you will see in there, in the hands-on exercise directory, is multiple steps of an optimization of a transpose kernel. And each one of these directories, starting at step 1, has both the main, it has makefile, and it has the solution in there. Now the solution is usually, so the solution is another directory, and it's actually the starting point of the next step. So step 2 already contains the main.cu in step 2 contains the solution of the step 1. So you should be able to just follow through. If you get lost somewhere on the way, just jump into at the next level, and you should be fine. So if we go into step 1, and again we have main.cpp and the makefile. So yeah, what you want to do is just you want to make it. Before knowing what it actually does, just make it and run it, right? So this one will generate a binary called transpose, and with an app run -./transpose, assuming that you had gotten an allocation, it will show you some output. Basically, in this case, we're just using a single OMP thread. So it's a multi-threaded CPU application that performs a transpose of a matrix. Right now, we're just using a single thread. And it has a GPU implementation. And in both cases, we're getting something like, whatever, 0.5 GB a second bandwidth for this transpose operation. Knowing that we have something like 180 GB a second available on the GPU, we obviously hope that this can be improved. And so those are the individual steps that you are guided through in this exercise. So what you want to do is have a look at the actual code. And quickly running out of real estate here. Oops. So there's some CPP macro for error checking and so on. So you probably don't care about that one too much. But there's a reference implementation for the transpose called reference transpose, which is just your transpose on the CPU. It has a nested OpenMP parallel region. Probably not the most optimal implementation, but you see that yeah, it's a straightforward transpose where you're linearizing your array and you're copying from the from the ith row, the jth column into the jth row and the ith column. Now, what you can see here is that there is a whole bunch of to-dos. So here we have something called GPU transpose kernel. It doesn't contain any kernel at all. At the moment, it's just exactly the same as the reference implementation, now without OpenMP. And we have a driver function called GPU transpose. And then we have the main. And so here it's slightly convoluted, but basically this is our macro that just calls either reference transpose or it calls the function GPU transpose. So you don't really need to worry about the about this part. This is just to exercise the different versions of the code of the transpose function.
There are some to-dos further below, right? With this time kernel CUDA thing.
Right. So the time kernel CUDA thing is, as you remember, you need to move data to the GPU, and you need to get the data back from the GPU. So yeah, as it says here, right? You want to allocate the device memory, you want to copy data to the device. Then have a slightly different form of the of calling the function. Go. And again, the goal is not that you type a whole lot here. Have a look at the solutions. I mean, you have the solutions there for reference. But I think it's good to look at the to-dos just to figure out what steps are actually necessary to make this into a kernel that you can launch from the GPU or from the host side. And just in case you want to see a bit more performance on the CPU side, without exporting the OMP num threads, you're actually getting just a single OpenMP thread. So if you're doing export OMP num threads equals 16 and then launch app run with the -D option, you should get significantly higher performance. Actually, let's do that. So we have the transpose. Exporting OMP num threads equals 16. Remember, 30 has 16 cores per node. And app run -N1. We just want to have one node, but we want to have 16 threads. This should give us quite a bit higher performance. Remember, we used to have 0.4 gigabytes a second. That's the single-threaded performance. And now we're at about 4.5 gigabytes a second CPU bandwidth that we're observing for this transpose operation. Just for the impatient ones, let's go into the final solution. Oops. We rebuild here and run it. And we're still at about 4.5 gigabytes a second. But here now you can see all the different steps that you're guided through in this exercise. And I mean, at the end, we're getting to about 173 gigabytes a second for transpose on the GPU, which is obviously quite a bit higher than what you achieve on the CPU side. Now, we're not claiming that the CPU implementation is optimal. It's just a very rough OpenMP implementation. But still, the good thing here is that this is very close to the bandwidth that you would expect for any kind of memory bandwidth limited kernel on a K20X GPU. So maybe just at a very coarse level, what are the different optimizations that can be done? Right? We've done now this one to compile it with the initial flag or with our makefile. And step number one is to actually move it onto the GPU. So that's this first to do. You need to add the CUDA API calls for CUDA malloc, CUDA free, the mem copies, and you probably want to synchronize at the end. That's not absolutely necessary, but so the step 2 then does a first implementation that's actually parallel. But the parallelization is at the level that we have one thread per row, and we have n threads. As you know, that's not particularly efficient, but it helps us just to look into the different concepts. So this is the main.cu in step 2. So that's doing the this is the case where we do the transpose by using one thread per matrix row. Right, and you see here we're using 256 threads, number of rows divided by 256. That's our launch configuration. And each thread computes its linear index, and it reads in the matrix at the jth column and writes it out into the ith row. So you're doing one row at a time within a loop. And yeah, given that there's no dependency between the different elements here, it's fairly obvious that this could be done in parallel as well. And so instead of having just 256 independent threads, we could go to 256 times 256 independent threads. That gets us more into the range that we want to be at. See a lot of question marks. I see nobody typing. What's up? Are you guys tired? Or just confused?
Well, it's hard to what did you say, guesstimate, like what to do here? Because at one point you said that it might be more efficient to actually do some computations within this, right?
Exactly. Yep. Well, that's why, right, so this is just step number 2. So step number 1 was basically just to get something running on the GPU. And now, so this something was that we have 256 threads, each thread being responsible for an entire row of the matrix. Now, what is written here in step 2 is the to-do is to actually get to a 2D blocks and transpose now 2D. Let me put up the picture. Right, so running the solution for step 1, you will see a performance that's probably around these 7 gigabytes a second. Let's try that too. I probably jumped ahead too far, sorry. So step 1, let's go into the solution, make the solution there. And then app run minus N1 minus D16 transpose. And as you can see now, right, we have these 7.3 gigabytes a second that we get on the GPU. Mm-hmm. Correct. Let's check. So let's look at this. So you have main. So this is now the solution of step 1. And right. So our matrix size is 1024 by 1024. That's the overall matrix. Yes, that is an inconsistency there. Oops, sorry. Right, so the simplest form would be in this one, that you say you take 1024 threads, and you're calculating the number of rows divided by 1024. Exactly. Yeah. And yeah, so there's most likely an inconsistency that at one point the exercise was at 256 by 256 threads, and we bumped the size up. So let's see what I have here. So if we go into step 2, main.cu, and again the matrix size is 1024 by 1024, and the block size should actually be it should be 250. This one here is by 1024 1024. It shouldn't really make a huge difference in the performance. Yeah, so you're at the 4.9 instead of the 7 that were reported. But yeah, for later on, it should actually be correct, I'm pretty sure. Right, once you go to the 2D block, then you have the 32 by 32 thread blocks, which gives you the 1024. So there it. Yeah, so let's write it here. So no, let's put it this way. Let's put it up here. Right, so again, the launch configuration here is this is your grid size, so the number of thread blocks, and this is your thread block size. Now this means that each thread block now has 32 times 32 threads, so 1024 threads, set up in a way that is a 2D configuration. So 32 by 32 threads. This is one thread block. And then you have rows, which we had 1024 divided by 32, gives us, again, 32. So our overall grid is 32 thread blocks times 32 thread blocks. A thread inside this thread block, this guy here, if it wants to figure out its linear index, well, yeah, it could determine its linear index. What is a linear index inside the thread block of this one here? Well, it's thread ID x.x, right, plus thread ID x times y dot y times block dim dot x. Right. So it's your block dimension in x, this one, times the number of rows. So this one here is my thread ID x dot y, and this one here is my thread IDX dot X. Now, in this particular case, you probably don't want to compute the linear index, but it's much easier to just keep the two-dimensional indices, the X and the Y index. Right? You're saying my global X index is my thread index plus the block index in X times the block dimension. So this gives me my global I. And the second line gives me the global J. Now, depending on where we're counting from, let's count from the top. So this is my global J. And we're still computing the linear index at the end to look up the data from in, to read in the data from in. But now we're taking J times cols, and cols is the number of our master matrix, not of our small block. So this one is cols. Which is 1024. Does that make any sense at all? So yeah, sorry for the confusion with the 256 and the 1024. It's just the two first examples that still use the 1020. Yeah.
So here basically we're mapping our matrix
Right.
my question is, if we map in a different way, or will we get the same performance or not? Is something inside that
Well, so what would be another mapping? Any suggestions? Yeah, I mean, so let's be creative. We said we have 1,024 threads, right? I mean, the obvious one that we did at the beginning is where we're just using a row per thread block, okay? Now, what happens in this case with one row per thread block is that when we are reading the matrix, everything is fine, right? Where adjacent threads in my thread block are accessing adjacent elements. I'm seeing this becoming a very densely populated chart, but just wait, I'm soon going to pull out the second color. But, and I might use the backside of this one soon. But when we're writing it, right, when we write it then out in this form, when you think about it in linear memory, what does that mean? Right, we have in linear memory, well, at reading time, we just got one chunk of data and sucked it in. At time of writing, we're writing out an element here, an element here, an element here, and an element there. So there's huge gaps in between. Now, what happens with our memory system is that every time we write these elements, we're actually writing at least 32 bytes, or reading. I mean, you can, whatever we're saying now for reading and writing, you can flip it around. It's exactly the same thing, but it's going to be at least 32 elements. So let's see, what are we using here actually? It's float, so it's only 4. So we're writing 4 elements, or 4 bytes. We want to write 4 bytes, but we're actually writing 32. So we're writing a huge chunk around. So all these 32 bytes will go across the wires to the memory system. And just at that point, it will say, oh, I don't need most of it except for these 4 bytes. So we're introducing a huge gap here. And what that means is that what is 4 out of 32? That's 1/8, right? So we're using only 1/8 of our bandwidth. So instead of the available, whatever, 180 gigabytes a second, we get at most whatever 1/8 of that is. So even if you would be writing your code optimally, that's not going to be very good. So now the question is, how can you fix that? Right? We said either you're reading contiguous and writing scattered, or you're reading scattered and writing contiguous. Both are bad. So what you want to do is now having a 2D thread block, which allows you both to read contiguous, you store it into shared memory, and then you can write contiguously as well. Right? Because when you're looking at this chunk here, how does this look in global memory? Well, it's not as big as this chunk we had here. For the contiguous chunk is smaller, right? It's probably this wide. But on the next line, this one might be far away, but we have, again, a contiguous chunk that's sizable. And we have 32 threads, each one writing 4 bytes. So that's obviously more than just 32 bytes. So again, we're getting almost perfect write performance. It's nicely contiguous in memory, all perfect. And it's also at read time when reading in a contiguous chunk of data. So that's why in this particular case, you probably want to have a 2D thread, a 2D thread block. Now, whether it's better to have 32 by 32 or 16 by 16, that's then further optimizations that we can look at. But conceptually, with having a 2D thread block, that gives us the ability to both read and write data in a contiguous fashion. So again, I think the question came up before, how do you decide whether you want to have a 1D thread block or a 2D? Again, here we're inherently operating on 2D data structures. So there's a likelihood that having a 2D grid or a 2D thread block could actually help you. I mean, that's a very vague, that's not the true argument, but it's just, you might want to explore a 2D thread block at that point. Now, right? The way it's written in this particular form, we're still ending up in the situation that at the time of reading, we're reading these elements contiguously. But at the time of writing, we're writing them out in a spread fashion. Right? Because, well, we're reading in one of the top row here, and then we're writing them out in that order. Optimal. That's why it says there that to do is you want to stage that through shared memory. So let's get to the other side here. again, it might be helpful to just look at the 2D picture and the 1D memory layout. So when we look at whatever, this row here, right, we're reading a contiguous chunk of memory from global memory. But the way it's currently written there is that my I index for the output goes over rows. So my I actually jumps from whatever, from here, if I'm writing this out, on the right, at the time of writing, I'm spitting out an element here, here, and here. So this is still poor. This is not optimal. But what we can do is we're reading in this data, this contiguous chunk. And then we transpose it in shared memory. So let's put an extra data, an extra stage here. Nah, sorry. Not sure if you can read that, but running out of space already. So what you want to do is you have your shared memory and you're writing the data in such a way that you're writing your scattered stuff out for this row. So this is my result, but now written to shared memory. And down for the next row, the green row, it also writes it out into shared memory, and again scattered. Now, writing to shared memory in a scattered fashion doesn't cost a whole lot. It's not optimal. It's actually, yeah, it is optimal if you're writing it in a scattered fashion to shared memory. So what we then end up with is in our, and that we do that for all the rows. And so we end up with having this interleaved pattern of the output elements in shared memory. And once we're done with all that, once we basically transpose our input in shared memory, we're now writing it back out in large chunks. So that we get this guy out and this guy out there in a contiguous fashion. Any sense at all? Okay, so I hope it became apparent, or that the problem itself is somewhat understandable, right? We're reading in a contiguous fashion. If we're just looking at one, if we're looking at the if you're looking at the adjacent threads at reading time, they're reading from adjacent locations. Adjacent threads at writing time write to scattered locations. Okay, and let's just use that as an axiom that's bad. Okay. It's not me. Yeah, exactly. Okay, so our how should I present it? Let's try it in another way. And oops. I have 4 colors, so that should work out somehow. Okay. At input time, we have thread 0, thread 1, thread 2, and thread 3. Okay? When reading, we have 0, 1, 2, and 3. Okay, nice and adjacent threads. So these numbers are the thread IDs. For writing, we would have so we end up with 0, 1, 2, and 3. Okay. So that's not what we want. So we put up shared memory. So again, we read these guys in, and we have SMEM. So now instead of writing straight to global memory, we're writing into shared memory the same amount of data. With gaps, with all of it. Then we continue. We take the next row. So this would be, so we first have worked on those guys and transposed it. Now we're reading in the next row and put it there in the second column. So over here, it would be 0, 1, 2, and 3. If we write this back out into shared memory, we're ending up with 0 here, 1, 2, and 3. Okay? That's not what we have in shared memory. And we repeat that for the entire duration. So we end up with 4 zeros. We end up with 4 ones, and so on. Okay, that's what we've written into shared memory. Now, we have everything in the right order to just copy it back out from shared memory into global memory. Okay, all we need to make sure now is that we let adjacent threads write to adjacent memory locations. So we're letting thread number 0 still tackle the 0th element. We let thread number 1 tackle the first element, the second, and the third. So in the first transaction, we're now just copying this guy up here into the output. 0, 1. 2 and 3. Okay? Well, those were the threads that wrote it, but actually we get the elements that were all processed by thread 0, or that were all originally read by thread 0. So that was the first transaction, and then we do a second transaction for all the elements that were read by thread 1 that now go out again by writing from 0, 1, 2, and 3. And they might now go into this, up here, so in this chunk. Okay? So we've read everything contiguously. We've written in a non-contiguous form to shared memory. But once we had all the matrix loaded in, we're writing back the global memory in a contiguous fashion. Does it dawn, not dawn? This is a very typical pattern. That's right. And you can view it also as a way of transforming between a structure of arrays into an array of structures. The other way around. You would do exactly the same thing, right? You're loading in contiguous chunks. You're putting into shared memory. Then you'd make any kind of crazy access patterns as you need. But then you're putting it back in order and write it back out in nice contiguous chunks. That's the whole magic behind it. The good thing is you can blame the compiler for doing it. I mean, you would hope that the compiler does it. Actually, I think I never tried to do a transpose in OpenACC by hand. Would be an interesting exercise. Yeah, I mean, one thing certainly would be to look at the performance. The other thing is that you get additional output from OpenACC. So if you, depending on the compiler you're using, but right, it would tell you something like it has been caching the data in shared memory. So that would be one indicator that happened. Yeah, it would be interesting to just give it a try. Again, the beauty is that you're deferring the responsibility of doing something clever from yourself to the compiler. So let's look at the at the example here. So in step 4, we have this implementation with the shared memory. And here is the actual implementation. So we create this shared memory segment called tile that has a tile dim, and that's 32, conveniently just the dimension of our grid. And so here we go. We have again the global indices I and j, and we are reading from this linear index into our two-dimensional tile, right? And here again, you can see the convenience of having two-dimensional thread IDs. It immediately gives us the IDs for the x and y of our local tile. It's just easier than having to mess around with modulos to divide things around. And then comes the important part. Now you want to have sync threads because you want to make sure that all the data has been loaded into your tile before you progress, right? Now we're computing the I and the j indices in a flipped form. But again, the I is now the one that is contiguous in the X thread index. And so we are writing out contiguously in I, and we have a stride in J. And we're writing out the thread X. So we're transposing here. I mean, here is where the transpose happens, right? We're reading here into a contiguous chunk in shared memory, and we're writing out in a transposed way, but to a contiguous location in global memory.
So what are we doing at grade I and J?
It's for clarity. It's not, yeah, and it's not recalculated. I mean, you have up here, you have it's the same thing. Well, yeah, it's different in the sense that you have the X and the Y's flipped here, right? So, I mean, maybe we've had, that's probably just something that you want to have a look at before going to bed or so, and put it under the pillow. But the key message here is that the approach that you've taken is you try to read and write to global memory in a nice fashion. And you're trying to do all kind of messing around with the data structure in shared memory. That's what you have shared memory for. So that's message one. And message two is, in those cases, you usually need to have a sync thread somewhere in your kernel, because you need to make sure that everything has been loaded before you start the next phase. If you had just a single warp in your that was executing the block, you wouldn't actually need the sync threads, because the warp just executes one instruction at a time. But here, you don't know at what point which warp of your thread block is being executed. And so in the worst case, what would happen is that warp number 0, the first one, just runs through all the way to the output. And at that point, your shared memory doesn't even contain the data from the other warps were supposed to load. That's why you have to have this sync threads in between. And you should go for a tour now. Options, we talked about the ones for the architecture. There is a flag for turning on debugging symbols. That can be helpful when you use debugger. I would assume that was covered as well. So capital G is just the GPU equivalent to lowercase g for turning on debug symbols. There's also the -- line info option that adds line information to the PTX code, so you can actually much better find out where some piece of code originated from in the source. Yeah, and this is just if you're really keen on, if you want to play around, you can compile with --CUDA, and you actually get the stripped down version of the, so you can use your own host compiler other than GCC if you want to. Now, NVCC is the front end that generates so-called PTX code. PTX code is our abstract assembly language that is portable between different generation GPUs. It's not directly interpreted by the machine, so it's not actual binary code, but it's a language that we then can compile into the actual binary code that runs on the machine. But in order to do that, we need an assembler And so that's PTX-AS. You usually don't need to worry about it, but it can be useful to, if you want to, especially if you want to figure so that was hard about the occupancy and the warps and those optimization steps. So I hope we can touch on that tomorrow again in one form or the other. Also, please feel free to catch me this afternoon or this evening if you have any remaining questions. I know those are somewhat confusing concepts, and as I said, now we have a whiteboard there, a flip chart, so that probably can help us to express the thoughts a bit more coherently. Otherwise, at least it makes up for nice pictures. In the next half hour, I'd like to just talk a bit more about the tools. There was talk of the debuggers, of DDT. The CUDA toolkit comes actually with a variety of different tools that might be helpful for your day-to-day work, especially when it comes to performance analysis and optimization. So I'll just cover those briefly. Basically, when you download the CUDA toolkit from the website, you get a bunch of development tools, libraries, debugger and performance analysis tools, and then when you're getting this for a Tesla board, then you also have access to the system management tools. So in the following, I'll just briefly introduce all of those. It's merely to give you an idea of what's behind each one of those names. And you can then later on go out and explore these tools in more detail, or ask questions about what could be done with those tools. So the first set of tools are the development tools. If you've already gotten to know NVCC, there's actually a few more options that we haven't covered yet. So NVCC is just our compiler wrapper that, to some degree, first off, splits the host and the device code. The host code is being handed off to your native host compiler, usually GCC on Linux boxes or CL on Windows boxes. And then it has the device compiler, so everything that eventually runs on the GPU will be compiled by an LLVM-based compiler. If you're a compiler guy, we have actually opened up a lot of this infrastructure. So if you want to write your own front end to GPU device code, if you have your own language that should generate GPU code, you can do that, and we offer LLVM-based library for that. So you can take LLVM intermediate language and spit out our language at the back end. It's also true in the other direction. You can parse CUDA and get it into the LLVM intermediate representation, and then it's up to you to generate whatever binary code you want. So if you have a fancy platform of your own, you can actually make a CUDA to your platform compiler. I'm not saying it's easy, but it's possible. You then have things like so those are the actual instructions that run on the GPU. Now, why would you want to do that? It can be helpful when you realize that something is just completely wrong, or you want to figure out is why do you see such a huge discrepancy between your theoretical performance model and the actual performance? Typical case is you assume that you're limited by memory bandwidth, but it turns out that you're not. What happens? Well, by looking at the SAS, you might figure out that you have a lot of casts between 32-bit floating point and 64-bit floating point. And they can be fairly expensive. So yeah, that can give you, looking at the SAS can help you identify such problems that otherwise are fairly tricky to find. Again, certainly not something to jump into at the very beginning. It's when you're really stuck and you have no clue how to make any progress with any other form, you might want to do that. The other thing is, I've also run into cases where you're compiling something and it's ridiculously fast. It's way faster at the code than you could ever imagine, or based on your theoretical models, you could ever understand why this happens. In those cases, it can also be helpful to look at the SAS because probably the compiler has eliminated tons of your code that, for whatever reason, it decided was not necessary to put in there. That actually can happen. I mean, a typical use case or a typical workflow for optimization is often that you figure out how many registers you're using. Because when you're first compiling your code from CUDA code via NVCC into PTX code, at that point, the compiler assumes an infinite register file. So it doesn't care about how many registers you're actually using. It's only at a time when you're invoking PTX AS where you do an actual register allocation, and that's when it can determine how many registers you're using, or your kernel will use. So when you're calling NVCC minus X PTX AS equals minus V, that's kind of probably the single most important part of this slide. With this one, you will get information about the register consumption of your kernel. So it will tell you that it's going to assume that you will need so and so many registers, and it will also tell you how much shared memory you're using and so on. So this can give you some information prior to running, some information about what resources you're going to use. Another tool that can be fairly helpful is at pretty low level, but it can be useful to look into that. It's called KUuptodump. So basically, it allows you to take binary code that was generated for the GPU and back assemble it and spit out the machine instructions. So this is for a given architecture. So once you've compiled it for instance, for the SM35 architecture, you can look at the binary and you see the true SAS instructions.